Okay, yesterday we finished the optics material that we're covering. Now we are going to come back and have one more thing that comes up about optics. What was the thing we did in lab yesterday? About
the wave nature.
The wave nature. That we had a couple experiments here that can only be explained if light is away, right? You can't explain polarization if it's particles, right? If you're throwing BBs, you can't say, ooh, the BBs are somehow randomly aligned like this, right? It has to be that they are waves. And likewise with the diffraction, the bending around the corners, and something I suppose I know I said this, I said you have constructive and destructive interference, and destructive and constructive interference only occurs with waves. Otherwise, you just have where a BB hits, there it is, and you build up the two piles. So that was the important outcome yesterday. Now we're going to start today with a new and really mind-bending topic, and that's relativity. So we're starting in on modern physics now. Everything up to here has been classical physics. And you probably are wondering, what's the difference between classical physics and modern physics, right? Okay, a couple people are with me. Yeah, what is the difference? At the turn of, not the last century, but the century before that, around 1900, physicists got really cocky. And there were a few of them that went on record saying, we've got it all figured out now. I mean, we might have a few more decimal places on the constants to get, but pretty much we've got the universe figured out. And then in 1905, this guy who was kind of a slacker in school and got a job working at the patent office wrote 3 papers.
How am I supposed to get a job at a patent office?
So Albert Einstein, who was very smart, I think we can all agree, but he wasn't the best student going through school because he didn't want to do what the teachers wanted him to do. A lot of us feel that way, and we're told, but that's the way the system works. Do what the teachers expect, and then you get out and you can, whatever. Right? You guys have dealt with that, right? Well, Einstein, much like Newton, was pretty much what he wanted to. So Einstein didn't like math. So he didn't go to math. He still went to take the test. He had a buddy who would tutor him the night before the test so he could pass them. But he got out of school, and then he got that job at the patent office that he considered the greatest job ever. Because he was very curious about how things work. And so people send their plans, and he looks through them and he's like, well, that'll never work, or wow, that's really interesting. That was his job. He thought it was great because he constantly looking at new things and getting new ideas. And then, as I've read, he and his friends would get together at the pub at night over a few ginger ales. They would, talk about the most recent articles in science and make fun of people who they thought made mistakes and whatnot.
Oh.
And then in 1905, he wrote his papers. Now, I don't think I've reviewed his papers with you before, have I? Okay, just have to make sure, because I've taught this class for 25 years or something crazy like that. You start reading who said what to. So he wrote 3 papers. One of them was explaining Brownian motion. Some of you have taken biology. Back in high school is where we learned about Brownian motion. Robert Brown noticed that when he had a little grain pollen floating on water and he looked at it through a microscope, something we recently learned about, that grain pollen was seen moving like this in the microscope. And so he described it as the result of cavorting beasties. That's what it said in my high school textbook, and that's what I stick with. What would cavorting beasties be? What would he mean?
Fluctuations in the atoms around there.
Okay, you're going with Einstein now. Don't be so advanced. He meant there must be some little microscopic critters in there that were making them move. But Einstein's paper said what DJ said. He said, no, it's because even though the water appears to be still water, those molecules themselves are bouncing around off of each other. And those pollens are so low in mass that you can actually see them rebounding from the collisions with the water molecules. And so he explained what that Brownian motion was on a physical sense, right? Brown was a biologist. He thought it was a biological origin. He said, no, it's just because it's not really stationary in water. The molecules are all moving. So that's his first paper. Now, I say first paper. I don't know what order they were published in or if they were all published the same day for that matter. I have a series of 3 articles. We submitted them all, I think, the same day. They're published over a span of a year. So the next article I'm going to talk about is the one on relativity. And it's a paper on special relativity. What we're going to look at today. That's not what he got his Nobel Prize for there. I have to look up, see if he got 2, but he got a Nobel Prize, at least his first one, if he got 2, for the last paper that was on the photoelectric effect. We'll study that later. We'll do an experiment on it. But the photoelectric effect was crazy because he said light is a particle. We just had a lab yesterday where you saw experiments that cannot be explained if light is a particle. And so Einstein produced an experiment. He didn't do the experiment. That's not what he did. He thought. But he said, if you do this, you should get this result. We'll study it later. And it's a result that's completely inconsistent with light being a wave, inconsistent with light being a particle. So 1905, when Einstein wrote these 3 papers, that's the birth of modern physics. Out of that, we have things like quantum mechanics and relativity. We have the ability to have transistors because of our understanding of quantum mechanics. And so that's what modern physics is. So we're starting our modern physics with relativity. So first, what is relativity? Relativity wasn't original with Einstein. We have what we call Galilean relativity. And here's an example of Galilean relativity. You have somebody in the airport on the little moving sidewalk. And somebody on the moving sidewalk measures and says they're moving at what, 1.3 meters per second with respect to me. But somebody that's standing out there in the bookstore or whatever, they look and they say that person's moving at a speed of 2.4 meters per second. Who is correct in their observation?
They are both correct in their reference frame. Same imagine the reference frame.
Okay. Just looking to see if he's reading. He's not. He's correct. TJ's been on a roll lately. Y'all notice? They're both correct. Relativity is the comparison of what you see in different reference frames. And so the relativity is how this relates to that. Now, just to throw some humor in there, because we're physicists and we've got great senses of humor. You might have heard Einstein's explanation of relativity. It says that if you put your hand on a hot stove and it's there for a second, it seems like an hour. But if you sit next to a pretty girl for an hour, it seems like a second. That's his description of relativity. Now, that's.
One day you'll find a picture.
Hey, he's got a pretty girl.
He just.
Okay. Anyway, let's stay on topic. So that's what we're saying with relativity is what's measured in one reference frame compared to another. What defines a reference frame? The situation you're sitting in. So you're sitting in the classroom. Your reference frame is this classroom. You would say that the screen is stationary, right? And as I mosey around in the classroom, you'd say, okay, Richard's moving. We could have somebody who is driving by in their car, and they say they're stationary in the car. And if they look through the window, they say, okay, all of the students in this classroom are moving as I'm stationary in my car. Now, most of us very fluidly switch between the reference frames. When you're in the car, you know that you're moving compared to the ground. And so you automatically say, I'm moving. But if you want to get a Dorito out of the bag that's sitting in the passenger seat, you don't try to compensate for the speed of the Dorito bag's moving, right? You say that Dorito bag is stationary with respect to you. So you fluidly are moving between a reference frame of the earth and a reference frame of the car, depending on what you're looking at. So that's what we're dealing with here. So one of the first things we have to define when we talk about relativity is an inertial reference frame. An inertial reference frame is a reference frame where Newton's first law applies. And at this point, I, as a student, got really nervous. I'm like, what? I thought Newton's laws were like fundamental. And now we're saying an inertial reference frame is one where they apply, which of course implies that there are reference frames where it doesn't. Well, remind me, your CNOW teacher, what is Newton's first law of motion? Yeah, it's up there, yeah. I think it's up there.
Things are stationary will remain stationary unless acted upon by force.
Yeah! Things will stay in constant motion unless acted on by an external force. So, and it has to be an external force is not equal to zero, clearly. So an inertial reference frame is a reference frame where if something is stationary, it's going to stay stationary unless something pushes on it. And if it's moving, it's going to stay at a constant speed unless something pushes on it. That's everything, right?
Now we've talked about Brownian motion.
Well, imagine this. Imagine you're in your sports car and you decide that you're going to put your soda up on the dash when you're sitting at the stoplight. And then when the light turns green, you put the hammer down. What's going to happen to that soda? It's going to slide back. It's not going to stay stationary in your car's reference frame. So that means your car was not an inertial reference frame when you hit the accelerator. Why was it not an inertial reference frame? Because your car was accelerating. If a reference frame is accelerating, then you're going to have Newton's first law. It doesn't work. Because if the reference frame accelerates, you still have inertia. That thing wants to stay put. But in your accelerating reference frame, it appears like it's accelerating. So that's the key to an inertial reference frame, a non-accelerating reference frame. So I have that all explained here, but it's a lot more fun to talk about than it is to read words, isn't it? Yeah, that's why we never read our books. Here's another example. Okay, I have to tell you what I think is a hilarious story. When I was in graduate school, if you go to graduate school in the sciences, anyone here considering going to graduate school in the sciences? Excellent, excellent. If you go to graduate school in the sciences, you are almost certainly not going to have to pay anything. They'll be paying you. But you have to do something for that. Your first year, they're just going to have you teach. Because, hey, you finished college. You know what life's about. And now, if you go to a public university, you might have lectures taught by first-year graduate students. There's a teacher that's right now at Washington University. She was in graduate school with me. Her brother was in college with me. They're twins. Weird, huh? Anyway, her first semester in graduate school, she was studying English, and she was teaching college English, or college writing, whatever you call it. And that's one of the things that we consider a positive if you come to a small school, whether it's a community college or union college, is that you're going to have teachers in all of your classes, not graduates. Anyway, so all of this, to get back to the story, we had a demonstrator for relativity, if you will. We had a seesaw that you could rotate on. And so you'd have two students sit on the two ends of the seesaw and rotate around slowly and toss a ball toward each other. And when you toss that ball, if you're rotating around, you want to toss the ball straight toward the person. But you're moving sideways, so when you toss it, because you're moving sideways, the ball is going to be moving at an angle like that instead of an angle like this. And so it appears to curve as you're on the rotating teeter-totter, or in this case, merry-go-round, right? I don't know why I get merry-go-rounds and carousels and stuff all confused in my head. So what we decided to do is to see if we could throw it to ourselves. Now, how are you going to throw it to yourself? Well, if I throw it up, it's going to go away from our circle.
Well, can't you like toss it up in the air where you're gonna be?
Yeah.
And catch it there?
But it has to have some toward the center aspect of it, right?
Unless you toss it up and you do one.
You do what? Well, I have to toss it up and to the left, or if I'm going to the right, up and to the left to counter my motion. Anyway, what we decided was I'm just going to throw it straight toward the center. If I go fast enough, I will come around and catch it. Totally cool idea, right? The only problem is, it's a teeter-totter with the base at the center. I was sitting on one side and one of my students on the other. Apparently, I was heavier than him. Now, I was skinny at that point, but I was still, my height, and most of you are, if you're shorter, you're not going to weigh as much. And so the whole apparatus slid in my direction. And so as I was coming toward a desk like this, I was like, oh no, and I leaned forward so it didn't hit me in the back, but the bench I was sitting on, the teeter-totter, hit this thing right here and broke it off. Now, I was nobody's fool. I took that table, jerked it around, put it up against the wall. But then I did tell the maintenance people I'd broken it. Because guys got to be honest at some point.
On my deathbed.
What? On your deathbed. Unlike the worst. Here's something that made me feel really stupid, okay? It doesn't have to do with relativity, but I have to tell you because I told that story. We had, for our office, we just had a lab room. And so we had like 5 of us in the lab room. And right underneath the light switch here, they had a fire extinguisher. And one day I came to flip the light and I went like that. And my hand hit the handle of the fire extinguisher hard enough. It had the little plastic pin. It sheared the plastic pin. That was embarrassing. Had to tell them that too. I initially just changed it with another room, and then I realized, wait, the fire extinguisher's there for a safety purpose. I'm okay, but if there's a fire in the other room, they're in trouble. Okay, so back to this. I'm sorry. I shouldn't go off on these tangents because you are paying for some important information here. Difference in inertial reference frame, non-inertial reference frame. What is the difference?
But not should we perceive?
Well, there is a difference in the perception, but it's the reference frame if it's accelerating or not. So why is the merry-go-round a non-inertial reference frame?
Because it's accelerating.
You're going in a circle, you're constantly changing direction, and that's an acceleration. Now, if you think about it, I'm going to say that this classroom is an inertial reference frame, that we're not accelerating. That's not 100% true. Give me some reasons why that's not 100% true.
The Earth is accelerating.
Okay? The Earth is accelerating. The Earth is doing an orbit around the sun, so we're changing direction. Also, the Earth is spinning on its axis, and so the surface of the Earth is accelerating. Furthermore, the solar system is orbiting the Milky Way galaxy, and so the solar system is accelerating. And so how in the world can we even pretend that this is an inertial reference frame? We have all of those different accelerations. By the way, if you watch flat earther propaganda, they'll make a big deal about this. How do we, they don't, not relativity-wise, but how ridiculous it is for us to pretend that we're doing all these things. How do we pretend that the Earth is an inertial reference frame?
Because it's what basically matters for a lot of what we're doing.
Yes, but that would not be sufficient. I mean, that would be a reason we would want to, but it's not sufficient to say we can treat it as inertial.
There's something is accelerating. You have two things in the reference to the other, is what I'm guessing. I don't know if you know what I mean.
I know what you mean, but it's a matter of scale. How big are we accelerating? Not very much. And so because our acceleration is so small, we treat it as having zero acceleration. So I just have to point out this technicality so somewhere down the line, you don't come to this realization and say, my teacher lied to me, it was all a lie. Right? We're not a truly inertial reference frame, but we're very close, and so we do calculations as if we are. So let's analyze these different situations, and of course, we're not doing this as a clicker quiz, we're doing it by everybody giving their input. So a stationary car, is that inertial or non-inertial? Okay, DJ says inertial. DJ said a lot of things today. He's been right every time, he is this time too. What makes it inertial?
Stationary.
Well, what term are we using to determine if it's inertial or not? It's not accelerated. Okay, what about a car traveling at constant velocity? Someone besides DJ. We don't want him to give us all the right answers. Okay. It's always important to realize constant velocity is still not accelerating, still inertial. Because oftentimes our brains just go to moving and non-moving and forget that constant motion is not accelerating. A car accelerating along a straight road. As long as we remember that accelerating is the big word, that's easy. And how about a car going around a curve at a constant speed? Non-inertial. Not non-inertial. How many people have seen Bill and Ted's Excellent Adventure? Non-inertial. That was one of their jokes. It's very highbrow humor. So let's get into these postulates of relativity. I know I'm going at a turtle's pace today. This here is not the postulates of relativity like it says at the top, but it has an important statement here about the Earth, treating it as inertial. If the Earth was truly inertial, we wouldn't have things like tornadoes. The tornadoes are caused by what we call the Coriolis force, a fictitious force. We talked about that at the end of first semester, right? Because you have a different speed, a different latitude on the Earth, and that makes you have a differential rotation. Okay. Yeah, this isn't adding really anything. If it just says any reference frame that moves with constant velocity with respect to an inertial reference frame is also inertial, right? It's pretty obvious. Let's this is the bottom part is to take our first situation with the person in the airport on the traveling sidewalk. If the person in the store is inertial and they see the person moving at constant speed on the moving sidewalk, then the moving sidewalk's also inertial, is what that's saying. Now a question that is a first relativity calculation. A bus is traveling 20 meters per second and a student walks toward the front of the bus at 2 meters per second. How fast is the student walking with respect to the ground? So that 20 meters per second is with respect to the ground. The 2 meters per second is with respect to the bus. How fast is the person moving with respect to the ground? Oh, we have two answers. So we have the speed of the bus with respect to the Earth. We have the speed of the student with respect to the bus. And Galilean relativity, which is everything that we know up to this point, says that the speed of the student with respect to the Earth is equal to the speed of the student with respect to the bus plus the speed of the bus with respect to the Earth. Now I'm going to put vector signs on this because it's a vector relationship. That's Galilean relativity. And if you want to make sure you get it right, all you have to do is make sure that those two indices are the same and that The first index is the first one here, and the second index is the last one here. That's the way Galilean relativity works. So if I had the speed of if I wanted the speed of the Earth with respect to the student, then I would have the speed of the Earth with respect to the bus plus the speed of the bus with respect to the student. Right? You make sure that you have the same index on the middle and that the outer ones are what you're looking for. So I'm going to write that down. The speed of the Earth with respect to the student is going to be speed of the Earth with respect to the bus plus the speed of the bus with respect to the student. Right, you have the same, inner ones are the same, first of the first and last of the last. But then how would you get speed of the Earth with respect to the bus? If the bus is going 20 meters per second in that direction with respect to the Earth, how is the Earth moving with respect to the bus? It's the same magnitude, but in the opposite direction. So you also have a rule that says VAB is equal to minus VBA. So with all of this in mind, which answer would I get here using Galilean relativity? If SB is 20 and SB is 2 and VBE is 20, what do I get? Say it out loud. 22, yes. 20 plus 2 is 22. So 22 meters per second is the answer that any normal human would give you. Nathan?
So I guess you missed it. I thought the person was outside of the bus.
Oh, no. It's a student in the bus.
I was thinking he was saying like it was walking towards the front of the bus.
Oh,
yeah.
Okay.
Like they're going to meet each other?
Yeah.
That's what I
That's what I thought.
Yeah.
Okay, that would be a completely different question. I did not think about that interpretation. Before they die.
That's why I was walking
Before they die.
Yes, the student was in the bus walking toward the front.
I think.
Okay.
I am sorry about that.
Good
Good thing that's not a test question for today, right?
I thought it was like.
Okay. And remember, if you have a question on the test that you're not sure you're interpreting it right, make sure you ask me. I'm sure everybody thought they were interpreting it right, and it was different from the way I intended it. If that's the case, let me know afterward. We'll try to find something that's fair, right? Because nobody wants to miss points because, well, I thought you were asking a completely different question. All right. Part B of this question. A spaceship is traveling at 0.80 c. What does c represent? Speed of light. Relative to the Earth, and fires a torpedo forward. I got these so the words are clear. At 0.40 c relative to the spaceship. So I'm going to write this down with subscripts for you. What was that? Nope. The speed of the spaceship with respect to Earth is equal to 0.80 c. Forward, okay, forward. The speed of the torpedo with respect to the spaceship is equal to 0.40 c. Forward. What is V torpedo Earth? So what do we think? We, as a group? Yeah, that's why I put TS.
I think it's 1.2.
Okay, Galilean relativity says.
Oh wait, it's C. It's faster than that.
Right, that's the same rules we just used before. the first one. Oh, that is the same color. I swear I hit the... I'm just not good at tapping stuff. And then the two in the middle are the same. And if we add the numbers, notice this is 0.40 C plus 0.80 C. And so we get 1.20 C if you wanted to have correct sig figs. That ain't right. That's not right because experimentally, people started trying to learn about electromagnetic waves, and they had some theories. We know that if it's a transverse wave, well, if it's a wave, it has to have a medium. Right? Sound waves, if you have a vacuum, there's no sound wave. Everything has to have a medium. And so scientists proposed that light must have a medium. But using a vacuum chamber, they saw light goes through the vacuum chamber. It doesn't turn dark when you suck out the air. And so they're like, okay, there's something else that we don't know about. Must be some ethereal thing. So they called it the ether. And so we have this ether theory that says the medium that the electromagnetic waves are traveling through is this ether. And you guys have learned enough about the scientific method at this point. Once you propose there's an ether, you've got to learn about it. And so they said, well, okay, if we had sound in air, if the air is traveling this direction, then my sound wave is going to actually travel faster that direction than it would this direction. Because when it's going with the medium, it's going to be traveling, well, the speed in the medium is constant. And so if the medium is moving, it's going to go faster in the direction the medium is moving, slower the other direction. And so they started doing experiments like, okay, let's measure the speed of light in this direction, the speed of light in this direction, so we can measure what the drift velocity of the medium is. But they got the same, no matter what angles they chose. Like, okay, well, maybe this medium is stationary. Let's move something. So let's take our device and put it on like a track that's going to move really smoothly, and then have the cart travel down that track and measure the difference in the speeds. Same thing. What they found is the speed of light in a vacuum is always 2.99792.458 meters per second. It's always that. Doesn't matter how fast anything is going, what direction you measure. And so they decide, well, we must have been wrong. There is no ether. It's just that light travels through a vacuum, and that's the speed of light in vacuum. And as a corollary to that rule, nothing can exceed the speed of light. 1.2 C would be exceeding the speed of light in vacuum. Nothing can exceed the speed of light in vacuum. You can have a medium where light goes slowly and then things can go faster than that. So this answer is wrong, which is troubling, isn't it? And that's where we first get to the mind-bending part of relativity. Relativity says that apparently this Galilean addition of velocities is simplistic. It works for everything we do in life, but it doesn't work when you're getting close to the speed of light. And so special relativity is the physics we have to apply when we're moving close to the speed of light. As a rule of thumb, if you're moving more than about 10% the speed of light, you have to use relativity. My car's never going to do that. I'm never going to have to worry about it. But for things, well, many other things, you do have to worry about it. So, this is what I've just spoken about for 5 minutes. Moving on. Since the speed of light in vacuum has to be the same in all reference frames, then we have an interesting question here. But first I'm going to entertain Leslie's question.
So can you repeat that again? You said if we're getting closer to 10% of the...
If the speed of something is higher than 10% the speed of light, you have
So
to
10% higher than the speed of light, though?
No.
Or
10% up.
Okay.
So the speed of light is roughly 3 times 10 to the 8 meters per second. If you get up to the ballpark of 10 to the minus 7, or 10 to the plus 7, not minus, 10 to the 7 meters per second, then you need to use relativity calculations. So here's a picture with a simplistic idea. I have a car that's traveling at a high speed, like 0.8 times the speed of light. It turns on its headlights. How fast is the light going to travel? If you're on the Earth, how fast is the light going to travel? Speed of light. If you're the driver of the car, how fast is the light going to travel? That's a little concerning. That doesn't make sense. Einstein started thinking, okay, so what if this car goes the speed of light? Then what happens? Oh. Well, there are two different ways of looking at
Why did it
this.
just impose itself upon itself?
There are two ways of looking at this. One is, okay, so the car's going the speed of light, the light's going the speed of light. That means to the person driving the car, the light must be stationary because it's going the same speed as the car. So the person could conceivably, get out there and look and say, oh, look, here the electric field's like this, there it's getting smaller, now it's like this. And then just see stationary electric fields in the light. But that's not a wave. Right? You can't have a wave with the stationary. It has to be traveling. It has to be changing. Remember Maxwell's equations. Changing electric field produced a magnetic field and so on. So that didn't work. And if the person in the car sees the light traveling away at the speed of light, it seemed to not work. This is a good enough question. When I was in graduate school, I went to a comedy club. Some random stranger sitting next to me, somehow we got into this topic, and our conversation got so animated the comedian had to ask us to shut up. It's something that's really kind of mind-bending. So we'll get to, before the end of the day, Einstein's solution to this. But first we have his postulates of special relativity. Postulate number 1. The laws of physics are the same in all inertial reference frames. So everything we've learned, Newton's second law, for instance, should be correct. Now, as we'll see later, you have to use the right form of Newton's second law for it to be correct. But all of the physics we've learned has to be correct. And then the second postulate, the speed of light in vacuum, is the same in all inertial reference frames. So we have those two postulates, and with that, Einstein set forward to figure out what is going on. And you will find people who still think that relativity is wrong, just like you find flat earth people. They probably are the same people. There's probably a strong union between those two groups. And so an outcome, a very quick outcome, was our intuitive understanding of nature is going to break when we do relativity. It's going to break our intuition, which makes this, like I said, mind-bending. It's been confirmed by lots and lots of experiments. I won't give you the experiments right now. In 1915, Einstein published another paper on a general theory of relativity. The general theory of relativity covers non-inertial systems. The special is only inertial, and that's all we're going to really study. But the general is important. The general theory of relativity says that things like gravitation is really the result of the warping of the space-time continuum caused by mass. You have the space-time continuum. In physics, we talk about things, events. Events have a location, x, y, and z coordinates, and they have a time. And so these events have 4 variables. 3 of space, 1 of time. That's what the space-time continuum means. And if you have a massive object, it warps that space-time continuum, which means a straight line isn't straight. That's the bottom line of what it means to warp the space-time continuum. Is this observed? Absolutely. At times, we can look at the sun, and if we block out the sun, or as we had a year and a half ago, a solar eclipse, so something else is blocking out the sun. If things are just right, you can see a star on both sides of the sun. How is it possible for light, remember we learned the ray model of light. How is it possible for light from a star to appear on both sides of the sun? It was bent. It's warped by the sun's mass. The Earth has a smaller mass, but the Earth's mass also warps the space-time continuum. What does this mean? It means clocks that keep proper time on Earth don't keep proper time when they're orbiting the Earth. And so we have in our phones little GPS receivers. These GPS receivers are receiving signals from at least 3 satellites orbiting the Earth. And each satellite says, okay, you guys just aren't old enough for this, but when I was a kid, we used to call time, or popcorn, on our phones, and it would say, at the beep, the time is 11:40 and 30 seconds. Beep. That's essentially what these satellites are doing. They're sending a signal. Actually, they say, hi, I'm Bob, and at the beep, the time is 11:40 and 35 seconds. Beep. So they're identifying who they are and what the time is. But it takes time for the signals to get to you, and so you have your clock in your GPS system, and it takes the difference in times to calculate how far away it is. And so you have 3 of those. You get 3 distances, distances from 3 locations. If you know accurately the positions of the satellites, so your little GPS unit has constants in there so we can accurately calculate the position of any satellite, any of the GPS constellation, then it can determine exactly where you are by triangulation. But key to this whole thing is the satellites have to keep proper time. And those clocks are calibrated so they'll keep time when they're in orbit, because they don't keep proper time on Earth. Because of this warp in the space-time continuum, the rate at which the clocks have time passing is different when they're orbiting us than when they're on the surface of the Earth. And so they have to make corrections for the general relativity, the warp in the space-time continuum because of mass. They also have to make corrections for the speed at which the satellites are actually moving with respect to us as they orbit us. So calibrating those clocks is no simple feat, and it requires use of relativity calculations. A last thing before we get to Einstein's relativity is the correspondence principle. What we've seen here is a physics that breaks everything I taught you. The correspondence principle says any new theory that talks about what happens in some crazy regime, like in this case at the high speed limit, has to agree with our physics we've already learned in the normal everyday life. And so the results of our relativity, if we get to non-relativistic speeds like everyday speeds, it has to agree with what we've already done. Which means you could solve the problems we've been doing up to here using relativistic physics, but you don't have to. You can use what we've already used. That's the correspondence principle. The two agree in the classical realm. Okay, so let's get to Einstein's example. So this is Einstein's clock. Einstein said, okay, let's imagine a clock that's built in a train car. And the clock consists of a light bulb that flashes. And when the light bulb flashes, light's going to go across the train car, hit a mirror, and reflect back. And when the light is received on the way back, that's the time for a tick of the clock. Pretty simple, right? Right?
Right.
So I should have given myself more space here. I'm just going to have to make another page to complete my calculations. But I can do the time for the first one real easy. So the time for one tick, so I'm going to call that delta t 0. The time for one tick in the stationary, or if you're inside the train cart, is equal to the light has to go from here to here and back. So if d is the separation there, what's the total distance the light travels? 2d. Divided by the speed of light. Right, because time is distance over speed. So that's the time for one tick of the clock. Now here's where I didn't give myself room. Now if the train is moving and you're standing outside of the train, the light is emitted here, hits the mirror here, comes back here. The distance this light traveled is a larger distance. Right? It didn't just go straight across and back. It came at an angle. And so now we have to calculate what the time for a tick is there. So this is where I'm going to have to give myself another sheet of paper. I'm going to put in two, but I think I can do it in one without problem. So I have the light goes like this. This distance here was D. And this distance here, I'm going to call this L, is equal to the speed of the train. So I'm going to use V for the speed of the train, multiplied by delta T. Now, I did not put delta T 0. I put delta T for the time measured when the train is moving. And so that's how far the train travels in the time of one tick. Now, if the train travels that far in the time of one tick, what's the total distance that the light has to travel?
In which direction? Because it travels in two components.
Okay, so we have two pieces. They're symmetrical, so we count one. We do one and double it, right? And so what is this distance right here? I put the 2 there because we have to double. How do we get that distance?
We can do Pythagorean theorem.
Pythagorean theorem. So square root of d squared plus, well, it's going to be 1/2 L. So that's the total distance the light has to travel. It's a larger distance, but since the light travels at the speed of light in all reference frames, if it's a larger distance, what's that going to make delta T? Larger distance, same speed, longer time. So our delta T is going to be that distance over the speed of light. So that's going to be 2 square root of d squared plus v delta t over 2 squared all over the speed of light. Now notice I have delta t. Oh, I should have made 8.5 by 11 sheets and I didn't. Good thing I made 2. I have 2 delta t's in this equation. I want to solve for delta t. So how do I solve this bad boy for delta t? First step?
Isolate?
Well, no, not really. First step, I'm going to multiply by c over 2 on both sides so that the 2's cancel and the c's cancel here. So I have c delta t over 2 is equal to square root of d squared plus that stuff.
You can split both sides.
That's what I had, right? 2 delta. I got to make sure. Yeah, c delta t over 2. I got those. So square both sides. Now I've got the delta t, so I can combine them. So I'm just going to move this over here. So I have that. Now, I gave myself way too little space. I'm sorry. Where's 8.5 by 11? Okay, putting in a normal size sheet for the next one. So now with this equation here, notice I have delta t squared with everything. I've got to write it once again. So there I factored out the delta t, divide across. That's the easiest way to write it out. Or so there's our time measured on Earth when the train is moving for the tick. Whereas the time measured in the cart is always going to be this here. So I'm going to take that delta t0 is equal to 2d over c. Let's change colors. And look at this and say, well, I could write delta t is equal to 2d over c times 1 over the square root of 1 minus v over c quantity squared. But this right here is delta t0. So delta t is equal to delta t0 times gamma, where gamma is that thing in parentheses, 1 over the square root, 1 minus v over c quantity squared. Now we have to stop now because I'm a minute over, but this is the time dilation equation. Notice that factor gamma. V goes from 0 to c, so gamma, if v is 0, gamma is 1. If v is bigger than 0, gamma is getting larger. So delta t, the time measured by somebody on Earth, is always going to be greater than or equal to the time measured by somebody inside of that cart. I'm actually probably not going to give you any homework tonight because we didn't get to do any problems with this. So have a great day. I'll see you Friday.
So
I'm not going to give you homework.